Blast output files. Blast output file is a very long file having 3 parts. At the beginning, there will be some header information followed by a summary of the alignments. The alignments and then some additional summary parameters and statistics at the end. Here is a sample blast output file which shows the starting, middle and end parts only. The file starts with BLAST10 2.1.3, that is version and date, references, ID, database, etc. The middle part starts with alignment and the details such as species, length, strands, etc. are given. At the end, there is the human DNA sequence from clone, chromosome, etc. Now let's write code to parse BLAST output. First you separate the hits, then extract the sequence and finally you find the annotation showing the e-value statistic. Parsing BLAST output. To see if the DNA has any new matches against the DNA stored in the constantly growing databases, or to write a program to automatically perform a daily BLAST search and compare its results with those of the previous day, we need to parse the BLAST output file. Let's do a programming exercise to extract annotations and alignments by designing a main program and 2 subroutines. The subroutines parse BLAST and parse BLAST alignment use regular expressions to extract the various bits of data from a scalar string. The program extract annotation and alignments from BLAST output file is used to extract annotation and alignments from BLAST output file. The program starts with the declaration and initialization of variables. Parse BLAST function is called with beginning annotation, ending annotation, alignments and file name, where beginning annotation and ending annotation etc. are scalars and alignment is the hash. Now we can print the annotation just to check if we got it okay. The subroutine also initializes variables and it uses the statement BLAST output file to get the BLAST program output into an array from the file. The statement is $BLAST output file equal to join, get file data of file name. Then extract the beginning annotation, alignments and ending annotation. The main program calls the parsing subroutine and prints the results. The arguments initialized as empty are passed by reference. The subroutine parse BLAST does the top level parsing job of separating the 3 sections of a BLAST output file: the annotation at the beginning, the alignments in the middle and the annotation at the end. It then calls the parse BLAST alignment subroutine to extract the individual alignments from that middle alignment section. The data is first read in from the name file with our old subroutine, the get file data. Use the join function to store the array of file data into a scalar string. The 3 sections of the BLAST output file are separated by the statement $beginning annotation, $alignment section, $ending annotation equal to $BLAST output file and the regular expression / within brackets ** alignments /n and in the next brackets ** and in the final bracket symbol database */ms. The pattern match contains 3 parenthesized expressions. The first expression ** alignments /n, which is returned into $, beginning annotation. The next parenthesis **, which is saved in $alignment section, and the final parenthesis database **, which is saved in $, ending annotation. The use of double dollar instead of a single dollar at the beginning of 2 of these variables indicates that they are references to scalar variables. When they were passed in as arguments to the subroutine, they were preceded by a \, like parse BLAST backslash dollar beginning annotation, comma, backslash dollar ending annotation, comma, backslash percentage alignments, and dollar file name. Within the pass blast subroutine, those variables with only $1 are references to the scalar variables. They need an additional dollar to represent actual scalar variables. This is how references work. They need an additional special character to indicate what kinds of variables they are referenced to. So, a reference to a scalar variable needs to start with $, a reference to an array variable needs to start with $, and a reference to a hash variable needs to start with $. The regular expression in the previous code snippet matches everything up to the word alignments at the end of the line dot star caret alignments /n. Then everything for a while dot star, then a line that begins with 2 spaces and the word database, followed by the rest of the file caret database dot star. These 3 expressions in parentheses correspond to the 3 desired parts of the BLAST output file: the beginning annotation, the alignment section, and the ending annotation. The alignments saved in $alignment section are separated out by the subroutine pass blast alignment. This subroutine has one important loop. While $alignment section equal to the regular expression till slash caret greater than symbol dot star /n, and within parenthesis caret, and in the next parenthesis question mark exclamation greater than symbol joined with star /n plus /gm, and my value equal to $ampersand. My $key equal to split function with double slashes and the or / $value and 1. $alignment hash of key equal to $value. There are some new things to examine. The 5 lines comprise a while loop which keeps matching the pattern as many times as it appears in the string. Each time the program cycles through the loop, the pattern match finds the value or the entire alignment, then determines the key. The key and values are saved in the hash alignment hash. Here is an example of one of the matches that is found by this while loop when passing the BLAST output shown earlier. This text starts with a line beginning with a greater than character. In the complete BLAST output, sections like these follow one another. What we want to do is start matching from a line beginning with greater than symbol and include all following adjacent lines that don't start with a greater than character. It is also necessary to extract the identifier which appears between the first and second vertical bar character on the first line. Example AL353748.13 in this alignment. Let's look at the regular expression in detail. $alignment section equal to tilde / caret greater than symbol dot star /n within parenthesis caret and another parenthesis question mark exclamation greater than symbol and dot star /n plus /gm. This pattern match which appears in a while loop within the code has the modifier m for multiline. The m modifier allows caret to match any beginning of line inside the multiline string and dollar to match any end of line. The regular expression breaks down as follows. The first part is caret greater than symbol dot star /n. It looks for greater than symbol at the beginning of the BLAST output line followed by dot star which matches any quantity of anything except new lines up to the first new line. In other words, it matches the first line of the alignment. The rest of the regular expression is caret within parenthesis, question mark, exclamation, greater than symbol and close parenthesis, dot, star, slash n, plus. After the caret symbol, which matches the beginning of the line, you will see a negative look ahead assertion, question mark, exclamation, greater than symbol, which ensures that a greater than symbol doesn't follow. Next, the dot star matches all non-new line characters up to the final slash n at the end of the line. All of this is wrapped in parentheses with a surrounding plus so that you match all the available lines. Now that you have matched the entire alignment, you want to extract the key and populate the hash with your key and value. Within the while loop, the alignment that you just matched is automatically set by Perl as the value of the special variable $& and saved in the variable $value. Now you need to extract your key from the alignment. It can be found on the first line of the alignment stored in $value between the first and second vertical bar or OR symbols. Extracting this identifying key is done using the split function, which breaks the string into an array. The call to split is split within brackets / backslash or symbol, then / comma $value. This will split $value into pieces delimited by the vertical bar character. That is, the vertical bar symbol is used to determine where one list element ends and the next one begins. The vertical bar is a meta character and must be escaped as slash and bar by surrounding the call to split with parentheses and adding an array offset of within square brackets 1. You can isolate the key and save it into $key. Regular expressions have lots of complex features, but as a result, they can do lots of useful things. Some of the alignments include more than one aligned string. For instance, the alignment for IDAK 017941.1 is shown again here. To pass these alignments, we have to pass out each of the matched string, which in BLAST terminology are called high scoring pairs or HSPs. Each HSP also contains some annotation and then the HSP itself. We can pass each HSP into annotation, query string and subject string together with the starting and ending positions of the strings. More passing is possible by extracting specific features of the annotation as well as the locations of identical and non-identical bases in the HSP. Now let's modify the earlier program by adding two new subroutines. One to pass the alignments into their HSPs and the second to extract the sequences and their end positions. As usual, the program starts with variable declaration and initialization. We use the variables beginning annotation, ending annotation, the hash alignments and alignment scalar and file name to store the BLAST text file. And the HSPs is an array and expect, query, query language, subject range, etc. are initialized to empty. Now we will see the working of the program. The main program calls the pass BLAST subroutine to separate the annotation from the alignments in the BLAST output file. The next line fetches one of the alignments from the alignments hash, which is then used as the argument to the pass BLAST alignment HSP subroutine, which then returns an array of annotation and HSPs in the array HSPs. Here you can see that apart from returning an array on a scalar value, it can also return a hash. Finally, it does the lower level passing of an individual HSP by calling the extract HSP information subroutine, and the extracted parts of one of the HSPs are printed. But in this program, some subroutines call their arguments by reference. Others call them by value. The subroutine pass blast mixes several arguments and one of them is not a scalar type. Remember that this is a good practice to use call by reference in Perl. However, they can be designed to call their arguments by reference. The subroutine pass blast alignment HSP takes one of the alignments from the blast output and separates out the individual HSP string matches. The technique used is regular expressions operating on a single string that contains all the lines of the alignment is given as the input argument. The first regular expression passes out the annotation and the section containing the HSPs, that is beginning annotation and HSP section equal to alignment equal to the regular expression tilde / within parenthesis dot star question mark and in the next parenthesis caret score equal to dot star and / ms. The first parenthesis in the regular expression is dot star question mark. This is the non-greedy or minimal matching. Here it gobbles up everything before the first line that begins score equal to. This is the exact dividing line between the beginning annotation and the HSP string matches. The next loop and regular expression separates the individual HSP string matches. While HSP section equal to the regular expression tilde / and in the first parenthesis caret score equal to dot star / and the next parenthesis caret and within the next parenthesis question mark exclamation score equal to dot star / plus / gm and the body push HSP's $ampersand. This is the same kind of global string match in a while loop we have seen before. It keeps iterating as long as the match can be found. The other modifier /m is the multi-line modifier which enables the meta characters $ and caret to match before and after embedded new lines. The expression within the first pair of parentheses caret score equal to dot star / matches a line that begins score equal to, which is the kind of line that begins an HSP string match section. The code within the second pair of parentheses caret and the next parenthesis question mark exclamation score equal to close parenthesis dot star / plus matches one or more lines that do not begin with score equals. The question mark exclamation at the beginning of the embedded parenthesis is the negative look ahead assertion. So, in total the regular expression captures a line beginning with score equal to and all succeeding adjacent lines that don't begin with score equals.